Okay, good afternoon. Welcome to the Virtual Physics Department Colloquium. The, Given all of the inclement weather out here, one could worry that it's actually not very hospitable for the colloquium speaker, Anadi, the Canepa. However, she actually comes from the Chicago area, so this is actually balmy for her typically during the winter. It's my pleasure to introduce Anadi to you. Nadia and I first met when she was doing her doctorate at Purdue University. We were working together on the CDF experiment. It was an experiment that was studying high energy proton, antiproton collisions at the Fermilab tevatron. Already at that point, she was deeply involved in searching for new phenomena. At that time, searching for evidence of supersymmetry. She then took on a postdoctoral position at Penn, University of Pennsylvania, continuing her work on the CDF experiment. And then a couple of years later, was appointed a research scientist at the Triumph Laboratory in Vancouver, now starting to work on the ATLAS experiment, an experiment at the CERN Large Hadron Collider. They She joined the Atlas Canada group there, and then became increasingly or took on increasingly leadership roles within the experiment. And she worked her way through the ranks at Triumph, and continuing her work on Atlas till about 10 years ago when she was stolen away to become a research scientist at Fermilab, where she actually joined the competition to Atlas, the CMS experiment, also at the LHC. She continued her work, searching for new phenomena. At the same time, she took on increasing leadership roles within the community. Um, in 2018, she was appointed a senior scientist at Fermilab, and was becoming the increasingly influential within the community. She became the deputy spokesperson of CMS in 2024 and was just recently elected and is spokesperson designate for CMS starting this year. So she really is one of the leaders in the field, and over the course of the last number of years has played a key role in the development of what has become the European strategy for high energy physics, but really a roadmap for particle physics, the future of particle physics, the worldwide. So it's my pleasure to pass this on to Anadi. Welcome and enjoy the show.
Okay, thank you so much, Pekka. It was a very nice introduction. And thank you for the invitation. I'm really pleased to be here. Sorry, I cannot meet you all in person. So let me share my slides. Okay. I hope you can see them. Okay, so thank you again for the invitation. And today in this presentation, I would like to give an overview on the future of high energy physics. However, to set the stage, since this is a colloquium, so expect experts from different fields attending, I would like to start by recalling what energy physics is and starting from particle physics. So particle physics aims at studying the universe at its most fundamental level. So matter composition, so matter versus antimatter, visible matter, dark energy, studies of the forces, what forces exist, how they act on the fundamental particles, and then the time evolution of the universe. So from the Big Bang, when the universe was hot, it was dense, to today when it's cold, we have large structures being formed, and a possible evolution into the future. And in the context of particle physics, when we try to explore high energy scales, we tend to use colliders, and that's what we refer to as high energy physics in our lingo. So what are colliders. So we have accelerators. They accelerate high-intensity beams of particles. These particles are made to interact in one space point, so we achieve a very large energy density in that space point. And by achieving this large amount of large energy density, we achieve two different goals. On one side, we reproduce the conditions of the universe a few seconds or fraction of a second after the Big Bang. So if you wish, colliders take us back in time. At the same time, we also explore smaller and smaller distances, so we can operate colliders as microscopes to try and determine the fabric of the universe. And indeed, the colliders in the past, let's say 100 years, have led to key discoveries in particle physics. On the left-hand side, you can see in bold, in 1974, 4 charm quark, 77 the tau lepton, 79 gluon, 83 W and the Z bosons, 95 top quark at Fermilab, 2000 quark and gluon plasma, and then, of course, the capstone of our experimental program, the discovery of the Higgs boson in 2012. And a combination, if you wish, of the experimental advances and the theory insights have led to the formulation of the standard model of particles and fields, which is in a way a simple quantum theory of the dynamics and interactions of all the known fundamental particles. So as you know, the standard model contains three generations of fermions, quarks at the top left, leptons at the bottom, the gauge bosons that do mediate the interactions, and then the Lagrangian, which is shown on the right-hand side. Let me move this. That is shown on the right-hand side in its most simplic, in the simplest form, does include what we call the Higgs mechanism that gives mass to the gauge bosons and the fermions. And so far, the standard model has passed all the experimental tests with extraordinary precision. And one of our theorists, Fabio Valtoni, refers to the standard model as a triumph of reductionist philosophy applied to some of the most fundamental questions in particle physics. Yet, we have many open questions that remain, and some are in a way intrinsic to the standard model, so it's shortfalls of the models itself, and others are really beyond, so the standard model does not include even a possible solution. So within the standard model, we can look at the Higgs boson, which is obviously not just another particle. It's the only fundamental scalar particle that we have observed so far. So the natural question arises, is it a composite particle? Are there several Higgs bosons? And as I said before, in the Higgs mechanism provides masses, and the masses of the particles are proportional to the ground state of the Higgs field. Is that confirmed by our experimental measurements? So what is the real role of the Higgs in the electroweak symmetry breaking? And that is about the composition of the universe. If now we think about the evolution, we think about the so-called electroweak phase transition, where essentially the Higgs field changed from a symmetric shape, hot universe, to the broken shape, where it gets this bottle shape or Mexican hat when the universe becomes cold. So the question is, what is the order of this transition? The standard model does predict a phase order 2 transition, but for example, to explain baryogenesis, we would need order 1. So it's interesting to measure what the phase transition may be. And also we know that the universe sits at the edge, at the boundaries between stability and instability, and the Higgs does plays a role also in the evolution of the cosmos. And if we now look beyond the standard model, there are many fascinating open questions. So what is dark matter? Do the forces unify? Why do we have these three generations? How do neutrinos acquire mass? And how do we actually describe gravity? So even though we have a model that does describe extremely well the non-particles, we are really left with many open questions that do hint to the existence of another theory at other energy scales. So we do need colliders to continue operate and provide us with insights that can be used by the theory community. And as you all know, the currently operating collider is the LHC, Large Hadron Collider. It is in Geneva, Switzerland. So in red here, it's a drawing of the tunnel, Lake Geneva and the Alps in the back. So the LHC is the world's largest and most powerful particle accelerator, 27 kilometers circumference, 100-meter underground. It does accelerate protons and heavy ions, and that's extremely important. It has superconducting dipole magnets that bend the beam so that it keeps this almost circular path. And the beam is not continuous, it's in bunches, and the machine can host up to 2,400 bunches. And then close to the collision points, and we have 4 of them, we have superconducting quadrupole magnets that focus and squeeze the beams in a way that the probability for interaction increases. And the interaction takes place every 25 nanoseconds, so 40 megahertz rate. And the really major technology breakthrough in this machine was indeed the 15-meter long dipole magnets. They have a field of 8.4 Tesla, and we have over 1,000 of them. So this is really the jewel of the machine, if you wish. So the machine has been operating extremely well till it started at full energy in 2009. As you can see here, we present the data as a function of time. Our data is measured in so-called barns. We are in the regime of femtobarns. Barns is a centimeter to the minus 28. And we continuously accumulate more and more data every year at a higher and higher center mass energy. And what really impressive is that the machine has achieved, summing up all the data set, 500 inverse femtobarn, while up to now we were expecting 300 inverse femtobarn. So it's operating extremely well. And this is the data set of the proton collisions. As I said, we also collide heavy ions, and the machine has operated at different species, providing really a very broad and diverse program for heavy ions. So the LHC hosts 4 large experiments. ALICE, that primarily studies quark gluon plasma. LHCb, that studies, of course, B mesons, CP violation, and then the 2 large multi-purpose experiments, ATLAS and CMS. Canada is on ATLAS, especially the University of Toronto, so I won't discuss ATLAS. I'll focus a little bit more on CMS so you can compare the two and have an overview of what we are doing. So in few words, CMS stands for compact muon solenoid. This is a picture of the actual detector with overlaid the standard drawing that indicates how particles interact with our subsystems. If you wish, you can imagine the beam going into the monitor, into the screen, and interacting in the middle of the yellow subdetector, which is a tracker. Charged particle fly out isotropically and then travel through all the different subdetectors. So the key governing element of the design of the CMS detector, which is actually quite simple in its design, is this solenoid. So the objective of the founders of CMS was to have the largest possible solenoid to contain as many subdetectors as possible. And this is the gray circle that you see here. I don't know if you see my mouse. And as you can see, particles bend, of course, with one curvature within the field, and then they change curvature when they on the outside within the return field of the magnet. So the idea of CMS was to have the largest possible magnet to contain 2 key subdetectors. In yellow there is a tracker, lightweight subdetectors that should deflect as little as possible the charged particles, and it should detect the trajectory of these charged particles without essentially impacting their energy, so they should not release energy in the tracker. And then we have the calorimeters that instead destructively identify the particles by stopping them and measuring the energy they release. There is one special charged particle that flies through without major interaction, and that's the muon. It's a minimum ionizing particle. It traverses all the subdetectors, exits the magnet, and then encounters dedicated so-called muon chambers that, of course, detect the passage. So going just a tiny bit more into the details, so you compare the different technologies. In CMS, our tracker is fully silicon-based, and we have pixels close to the interaction point, and instead the long strips on the outside where we need less granularity. The electromagnetic calorimeter that is optimized to detect electrons and photons is made of lead tungsten bars. And then we have a hadronic calorimeter that is brass plus plastic scintillators, while Atlas, for example, has a liquid argon system for the calorimeter plus and tile calorimeter. We both use gaseous chambers for the muon detection with different techniques depending on the requirements that we want to deploy. And as I said, our interactions are every 25 nanoseconds, so 40 megahertz, and neither Atlas nor CMS won't be able to record this much data. It's simply too much data to be stored on disk and on tape. So we have a so-called trigger system. So it's an online subsystem that very quickly, within microsecond at the first stage, select events of interest and then send them for further processing. Again, CMS has a very streamlined, simple approach. We have a level 1 trigger, fully hardware-based. It receives the event at 40 megahertz and produces an output at 100 kilohertz by design. And then we have a set of commercial CPUs that receive the events that this first hardware system has selected, processes them, and then release at 1 kilohertz dose for permanent storage. What I want to highlight is that even though Atlas and CMS were designed in the late 90s and built in the 2000, we are continually upgrading, improving this detector to really fully exploit the potential of the machine that keeps on giving us collision data. And just as an example, here you see the evolution of our trigger system. By design at the start, we were collecting 1 kilohertz of events. Now we are collecting almost a factor of 30, so 27 kilohertz. And we even have a stream that select events at 40 megahertz or using anomaly detection. So we are really making the system extremely flexible in order to extract as much physics as we can with the technologies that become available as time passes by. And thanks to this really unique data set that the LHC has provided us, Atlas and CMS have been able to perform exquisite precision measurements of the Higgs boson, even though in a way just 10 years have passed since the discovery. So it's not too much if you think. And yet we have achieved per mil knowledge of the Higgs mass, precision characterization of what we call the discovery modes, so the probability for those processes to take place. We have a large enough data set that we can perform searches for very rare decay modes of the Higgs, achieve sensitivities much higher than anticipated. The plot at the bottom, for example, you don't have to stare into the details, but just gives you an idea of the monumental work that we are performing. This is a summary of the order 100 cross-sections, so probability for a given process to take place, measuring in 1,000 different decay modes. And on the right-hand side, you can see that we have been able to measure the coupling of the Higgs to bosons and the fermions, probing 3 orders of magnitude. So this is really a major achievement of the LHC experiments. And out of all the couplings, there is one which is extremely special, and it's the self-coupling, so the coupling of the Higgs boson to itself. Why is that special? Because as you can see on the right-hand side, it enters the Higgs potential, and the Higgs potential in turn is the one that determines whether or not our universe is in a stable, metastable, or unstable status. So as of today, we think that our universe sits in a metastable. It means that we are sitting in a local minimum, so there is a global minimum at a higher energy, and sooner or later, the universe will quantum tunnel into that global minimum. And knowing essentially the self-coupling will tell us the shape of the potential, so whether it keeps on growing or indeed it becomes negative, and then the universe can roll into another state, of course, at very high energy scales. So how can we measure this self-coupling? So at the LHC, we look for the pair production of Higgs boson. So the Feynman diagram is on the bottom right. As you can see here, kappa lambda is the coupling we are looking at. And the challenge here is that the process is very rare. So it happens 1,000 times less than the single Higgs. And in fact, before we started in this endeavor, the understanding, especially from the theory community, is that we would be overwhelmed by the background and we would not be able to measure this important parameter. And instead, we are making major step forwards because of the large data set and also because we are deploying in a very aggressive way AI ML at all stages of the data taking and data analysis. And here I selected a beautiful result by Atlas. So it's a search for the pair production of Higgs, where one Higgs decays into B quarks and another Higgs decays into two photons. It uses almost the entire data set at 13 and 13.6 TeV. And the plot here shows you the upper limit on the value of the lambda. What does it mean? It means that we have excluded the existence of values of the lambda, which is larger than 3.8, the standard model value, of course, at a given level of confidence. And this is really an unparalleled result that we could not even anticipate 5 years ago. And really the growth in the usage of advanced analysis techniques have enabled this. And of course, the LHC is also looking directly for new physics. I don't have the time to discuss that, so I just show you a few pictorial images of that. So we are looking for new phenomena in what I think is the most comprehensive search for new phenomena in a single facility done by CMS and Atlas. We're looking for light mass particles, heavy particles, complex decay modes, prompt, delayed, compressed spectra. And if you want to keep one main take-home message is that we have been able to probe the energy scale for many, many models of new physics up to 10 TeV, which is actually remarkable considering that we have at most 13.6 TeV available in the center of mass. So we are really pushing the boundaries of the energy frontier with this machine. So the question, and because of the breadth and the depth of the program, the CMS and Atlas, together with Alice and CMS, have been actually awarded the Breakthrough Prize for Particle Physics in 2025, which is actually quite, again, remarkable. So now what's next? So we do have a future collider, which is approved. It's an approved project, and it's called the high-luminosity LHC. So we are here, we are in 2026. The high-lumi LHC will start in 2030. It will run for 10 years approximately. And the objective is to deliver 3,000 inverse femtobarn, so a factor of 6 amount of data with respect to what we have now. So it's a significant increase with respect to what we have sitting on tape at the moment. And of course, how can we do that on a relatively short amount of time? The machine has been fully upgraded. It will have much higher intensity beams, leading to a very complex experimental environment at the different interaction points with up to 200 collision per bunch crossing to reconstruct by the experiments. We will run for 10 years, so we will accumulate a large amount of radiation. So we need to have really a paradigm shift in upgrading our detectors. So we need higher granularity, so better resolution, precision timing, radiation hardness, capacity to handle higher rate, and then extended coverage, so more forward coverage. So again, I won't mention Atlas because you're experts in that. Here it's a cartoon presenting the upgrade of CMS. If if you wish, in CMS, the only element that won't be touched is the magnet. We are replacing, upgrading all subsystems. And in particular, we have three major upgrade projects. We are replacing our entire tracker system with, again, a full silicon-based tracker. The major difference with respect to the current one is that that system will be self-triggering above 2 GeV in momentum. Much higher granularity. We are moving from 200 million to 2 billion channels to be read out, 40 megahertz. And then we have a major novel, innovative calorimeter in the forward region. It's called a high granularity calorimeter. It's a silicon-based. It means that we are really bringing in all the capabilities of a tracking detector into calorimetry. Higher granularity, we are moving from 600,000 to 6 million channels. And then we will have a new, so we didn't have it before, timing detector that will achieve a high precision timing on single charge tracks. And Atlas and CMS will be really new generations detector, will collect and analyze the largest proton-proton dataset ever delivered at the energy frontier. So thanks to that, we will be able to make major improvement on precision measurements of the standard model parameters, searches for new physics. And I want to show you here just two results to set the context for actually the main part of the talk. So thanks to this large data set, we anticipate the capability to measure the coupling of the Higgs boson to different particles at the percent level, so making a factor of 10 improvement with respect to the current knowledge. And especially we will reach above 7 sigma significance on the observation of the di-Higgs, so pair production of Higgs, which in turn can be translated into a 30% precision on the self-coupling. Again, this is truly unforeseen if we look back at what we expected at the time of our TDRs. So the question now is, what is the best machine? How can we continue the exploration of the energy frontier once we have collected this wealth of knowledge at the high luminosity? And to try and somehow visualize the answer, please have a look at this diagram. So we are looking for new physics, right? We can do it in two different ways. We can continue scanning higher and higher energy. So we build a collider with an energy higher than the LHC, as high as we can. So we essentially are walking along the x-axis, and then we look for an excess of events over a smooth background. So we look for a resonant peak corresponding to a new particle. And this is a simple explanation of what we call the direct search for BSM, beyond the standard model physics. Alternatively, we can decide to study the properties of the known particles, for example, the Z boson, the W boson, the Higgs boson. We can measure the coupling to other particles as precisely as we can. And by this precision measurement, we can try to see if we have any deviation. And usually, if there is a deviation, the deviation is proportional to 1 over the scale of new physics. So we want to measure these couplings or these properties as precise as we can, because the more precise we are, the more we probe a very high energy scale in terms of new physics. So in order to be precise, the optimal approach is to build a machine that produces only that particle, sits at that mass, and it provides also a very clean environment. Protons, as I said, they are not fundamental particles. So when we let them interact, what we actually observe is the interaction of gluon and quarks. We have a very complex underlying event. So they're very complex in terms of event. Instead, electron and positron are fundamental, so they're very clean and they allow very high precision measurement with low systematic uncertainties. So let me talk a little bit about this. So the idea of having a Higgs factory, so a machine that produces Higgs bosons in a very clean environment, so E plus, E minus. So usually, if we sit around a few hundred GeV, which is the scale of the mass of the particles we know, the cross-section are much lower than those at the LHC. For example, for a 250 GeV E plus E minus, we are talking about a reduction of a factor of 200. However, the events are much cleaner because we produce only the Higgs boson and there is nothing else essentially produced at the same time. And on the right-hand side, you can see the event display. So at the top, it's an E plus E minus event collision. On the right, it's a proton-proton collision. And on the left, just for information, a muon collision. So you see the E plus E minus is an image that we can almost reconstruct by eye. Also, a very important feature is that in an E plus E minus, we have a well-defined initial state. Again, they are fundamental particles, the two electrons, the electron and the positron. So we know the energy at the collision. So we have a total control of what we are producing. If we look down on the left-hand side, you see the production cross-section, so the probability for a given process to take place as a function of the energy of the collision. If you focus around 200 GeV, you'll see that the Higgs production is dominated by the process where the Higgs is produced together with the Z boson. And this is a very useful process because we know the energy of the incoming E plus E minus. We can fully reconstruct the mass of the Z. As a result, we can reconstruct the Higgs boson regardless of how it decays. We can reconstruct the width of the particle, something that we cannot do at the LHC, the total cross-section. We have access to the Higgs to ZZ coupling at a high level of precision. So a machine that sits at an energy scale that allows to produce a Z and a Higgs really brings in a lot of information regarding the Higgs. So what are the machines that are currently being proposed to be built at CERN? The first one is called the Future Circular Collider, FCCEE. It's a double ring collider. It's a new tunnel. So you see on the left-hand side the LHC, and then the 91-kilometer tunnel is the dotted line. Here you see the size and the region that it spans. It is foreseen to have 4 operating points, so it will run with energies compatible with the Z boson, with sitting at the Z boson, mass point, pole, WW, threshold, ZH, and TT bar. So we will be working at these 4 energy scales. It will have 4 interaction points, so we can host up to 4 detectors like the LHC. And what's important to keep in mind is that the RF installations, so the cavities, are identical across the 4 operating points. It means that we can switch from one running to the other. So we can run for a few years collecting Z bosons, then we can go WW, come back to the Z, and so on. The other option for a circular collider is called the LEP-free. LEP was the E plus E minus machine that was operating in the LHC tunnel before the LHC. LEP3 would still be in the LHC tunnel. It will operate at three points at the Z boson mass, WW and ZH. It will host only two interaction points, and it will have different cavities installation, so it won't be easy to switch from one energy scale to the other. The other proposals for E plus E minus are linear colliders. So on the left-hand side, you can see a linear collider facility called LCF, so the acronym. So the LCF is based on the ILC design that you are probably very aware of because it was proposed for a few 2 decades by now. It will sit in a 33 long kilometer tunnel. It will be based, of course, on superconducting radio frequency cavities. It will be able to operate at three energy scales at the Z pole, so producing a large amount of Z bosons, close to the ZH, and then at 550 GeV. It will have two interaction points, but because it's a linear collider, this, of course, we cannot have two detectors operating at the same point, so there is a push and pull technique, so we move the detector in and out of the beam. So essentially, the detectors are sharing the amount of luminosity. And on the right-hand side, it's the other proposal. It's called CLIC. It's also quite old by now. It's based on a two-beam accelerations. We extract the power from a high-intensity beam and transfer it to the high-energy beam. It's compact, so it's up to 15 kilometers in comparison to 33 for the LCF. Two operating points for the stage one, so 380 GeV and 550 GeV, two interaction points like the linear collider, the LCF. So let's look now at the comparison of the performance, just looking at the amount of data they can produce. And here I would like to remind you that when we are performing precision measurements or searches, what we are interested in is in maximizing the number of events associated to a given process. And in simple terms, the number of events is proportional to the probability of a given event to take place, sigma, the cross-section, times the amount of data that we have collected. So how many times we have actually tried to produce the event. So this is very important in subsequent message I would like to give. So if you look at this plot, you'll see that the circular collider, especially the FCC, provides much more data than the linear collider in the energy scale that we're talking about, so between 100 and, let's say, 350 GeV. And in fact, the FCC-EE gives a huge rates when it sits at the Z pole, so when it is tuned at 91.2 GeV and produces Z bosons. Just to give you a scale, it produces 10 to the fifth amount of data that we have collected with the previous LEP experiments. So 10 to the 12th Z, 10 to the 11 B, 10 to the 11 tau, and so on. The linear colliders do provide less luminosity. However, there is one important feature. We can polarize the beam, and by polarizing the beam, we can change the sigma. So we can change the production cross-section, so we can slightly rebalance the lack of the lower luminosity they offer, but not to the full extent. All these machines have been compared for the past several years, and especially with great focus in the past year through the European strategy. You can see in the table on the left, picking just two examples, that they do improve quite significantly on the achievements of the high luminosity LHC. For example, at high lumi, we cannot measure the total cross-section of the Higgs, while we can achieve a sub% precision at the Higgs factories. We measure the mass of the Higgs with a roughly 20 MeV precision, while we can go down as 3 MeV with the Higgs factory. Now, if we compare these machines across themselves, we start seeing that the FCC-EE, because of the large amount of data it collects when it transfers at the Z pole, WW threshold, ZH, does achieve the best precision. And we can go a little bit deeper and look at how well it does in studying the Higgs sector. So this is a busy plot, so I'll try to be slow. It shows the precision at which we can measure the different couplings of the Higgs, for example, Higgs to Z, Higgs to W, Higgs to gamma, and so on. In gray, it's the anticipated precision at the high luminosity LHC. So it's the starting point of the future colliders. And then you should compare the light green, light red, so those are the linear machine. Orange is lap-free, and then for the FCC, you should look at the darkish blue, so the middle square. You can see that overall, all the Higgs factories are able to bring the precision to the coupling at the 1% level. But then if you look a little bit, zoom in, you'll see that the FCCEE is the best machine as it offers a precision that is better by a few factors with respect to the linear colliders. And in terms of self-coupling, these Higgs factors cannot produce di-Higgs, so we can only probe that at the loop level, as shown here. So we can indirectly set a precision on this coupling at the level of 20%. So it's a marginal gain with respect to the LHC, because we expect that to be better than 20%. One important point I would like to highlight, even though you may have heard that we refer to low energy E plus E minus as a Higgs factories or Z, Terra Z factory, they're actually excellent machines to further our understanding of the electroweak sector, of the top quark, of the strong sector, and so on. An example is provided here. This plot shows you the precision on the measurement of the W boson mass and the top mass. Why are they relevant? Because they have an indirect impact on the trilinear coupling, on the mass of the Higgs. So in turn, they have an impact on the evolution of the universe as we increase the energy scale. As you can see in the insert, the future colliders will bring a major improvement in terms of precision in comparison to what we can achieve at high lumi, which is the light gray band. And out of all the future colliders, the best one remains the FCCEE, because it brings essentially an improvement in sensitivity of the order of factor 30 with respect to the linear collider. Even though, as I said, the depolarized beam and the linear colliders do offer sensitivity to chiral observable, so they partially compensate for this lower luminosity. Now, not only a W mass, top mass, the large Z sample at the FCCEE also allows us to measure, for example, the strong coupling very precisely. The strong, the alpha S is actually the least known of all the couplings. As you can see here in green, we are still at the level of 0.7%, while you see that the FCCEE in orange brings down the precision on that coupling at the level of 0.1%, which is truly remarkable. And having again a large sample of Z bosons allows us to do searches for new physics, for example, in the flavor sector. What I mean by that is that we produce a large amount of Z bosons. The Z decays into a tau, lepton, for example, and then we can look whether the tau decays into a mu gamma or in free mu. Those decays are highly suppressed in the standard model, so any excess of events will really be a manifestation of new physics. And here you have the upper limit, so if you wish, the sensitivity of the different machines. In blue are the so-called B factories that are, by construction, offering a large amount of Bs and taus. And you can see that the FCCEE, in green here and in pink here, does provide a significant improvement, or at least it's comparable to the sensitivity of designated machines. So now this covers a little bit to give you an idea about the capability of doing precision measurements and thus indirect searches for BSM. But as I said, of course, we have also an ambition to search for new physics directly so that we can really create a new particle and fully characterize it as we did, for example, for the Higgs boson at the LHC. So the question is, what are the high energy machines that are being proposed at the moment? So the first one is the FCC-HH, so hadron-hadron. This is a hadron-hadron machine, primarily proton-proton, that would operate in the same tunnel as the electron-positron machine, so the EE. We refer to this as FCC integrated program, so EE and proton-proton. Because of, thanks to the size of the machine, we can reach energy scales of roughly 100 TeV. At the moment, the baseline is 85, but we can reach up to 120 TeV, sorry. The CERN was charged with performing very thorough feasibility studies. They released the outcome in the spring of 2025. They demonstrated the feasibility of the machine. They did a series of geological studies. For example, you can see here up to 100 different placements of the machine to try and see what the best territory would be for that machine. The other option is to upgrade the linear collider that we could build as Higgs factories. One option is to upgrade the LCF. That can be done in the same tunnel, so we would not need to increase the length of the tunnel, so we would keep the 33.5 kilometer tunnel, and we would instrument the machine with more powerful SRF cavities, for example, increasing the gradient of the cavities, or using a completely different technology, the cool copper cavities that have been proposed a few years ago during this no mass process. The alternative is on the right-hand side. We could upgrade the click. So what you remember, it was a compact linear collider that requires extending the tunnel. So in order to reach 1.5 TeV, we will need a 29 kilometer long tunnel and a 50 kilometer for a 3 TeV machine. And more recently, we have seen a major push for the exploration of a machine that utilizes muons as beams in the machine. So this machine could be a muon collider at the 10 TeV scale. So why do we consider muons more attractive than electrons, for example? The reason is quite simple. They have reduced synchrotron radiation loss. It's suppressed proportional to the ratio of the masses. So we're talking about 10 to the ninth suppression with respect to electrons. It means that when they travel on a circular path, they lose less energy than the electrons would do on a same radius. It means that we can build a bigger machine for the same power. So they provide an alternative to electrons to really reach high energy. And also they are also in a way more sustainable than protons because they are fundamental particles. So the entire energy of the beam is available to us in the center of mass, while when we collide protons, what we really can use and benefit from is the energy of the constituents of the protons, so less than the energy of the beam. However, as you can guess, there is a major challenge, muons decay. So in the rest frame, they have a lifetime of 2 microseconds. It becomes a little bit longer, of course, when we go to higher energy, but that in turn places major constraints, requirements on the accelerator part and on the collider part of the entire facility and on the environment around the lab. So this is understudied. There is a lot of enthusiasm and push, but it's a machine that may not be really realizable on a short time scale. And I should highlight that even though there was a proposal to have it situated at CERN, at the moment, the most likely location is in North America at Fermilab. Okay, so let's move on now to comparing the capabilities of these machines. So as I said, these are discovery machines. The spectrum of models for new physics is very large, so I cannot and I would not want to compare all the different models for you. So I wanted to show you just the answer to two fundamental questions, the origin of the weak scale and the nature of dark matter. So the origin of the weak scale means why the Higgs is at such a low energy scale, why it is just 125 GeV. And I would like to do that in the context of a well-known model, so I don't have to explain it, which is supersymmetry. So supersymmetry, as you know, does predict the existence of partner particles to the standard model. So the way to look for that, for the existence or the realization of that model is to look for these new particles. And the plot here shows essentially the sensitivity of the different machines to the existence of those particles. So you don't need to really be worried about the different bins here, but you see that so the horizontal line, the gray line here, indicates the scale, the sensitivity, the current sensitivity of the LHC. And you see that the machines that are significantly extending that sensitivity are the FCC-HH in pink, and then the muon collider in yellow, and we are really able to probe up to tens of TeV that the existence of those particles for specific nature of the particles. So we're really pushing the boundaries with respect to the current knowledge or the knowledge the high lumi will have accumulated by 2040, really enabling for a major advance in our understanding. What about the Higgs, the self-coupling of the Higgs? If you remember, I said that the Higgs factories do not have enough energy or phase space to produce the Higgs, so we can only probe the self-coupling indirectly. Instead, at high energies, we can produce di-Higgs directly, and we can probe for the self-coupling directly. You can see on the left-hand side the anticipated precision on the measurement of the self-coupling. At high lumi, as I said, we can reach 25 GeV, 25%, apologies. A similar scale at the stage 1 Higgs factories, and really FCCHH and the muon collider are the two machines that are bringing really the ultimate measurement at the level of few percent precision. And on the right-hand side, you can see the impact of that precision on the knowledge of the shape of the potential. So the LHC now, it's known with this level of precision, so you can imagine that any shape of the potential may fit in this uncertainty bar. We improve at high lumi, and then we reach really a good understanding at the high energy colliders. Okay, so switching completely gears, what is the strategy? So what is the approach to really decide what machine will be built? We had different strategic planning exercises, first in the US and then the last one in Europe. So in the US, so the two processes in the US are quite old, so I just briefly remind you here. We had the so-called P5 process, which is launched by the Department of Energy and is essentially used by the Department of Energy to prioritize the projects. So it really helps the government decide how to invest the budget they have for science. So the P5 took place 21-22, and it contains two major recommendations to contribute to an offshore, so not in the US, but abroad, an offshore Higgs factory. And at that time, the two designs, the FCC-EE and the ILC, were considered to meet our scientific requirements. And then recommendation 4 indicated that we should establish an aggressive R&D to really determine a realistic path towards a high energy collider. And then the narrative indicated that the preference would be for a US machine, a muon collider. And that is reflected in a second strategic planning exercise of the National Academy of Science that also indicated our priority being building a US-based muon collider and then participating in a Higgs factory at CERN. And here we broke the symmetry, mentioning explicitly the FCC-EE. So how does the CERN actually define its strategic plan? It's governed by the CERN Council. So the CERN Council appoints a so-called physics preparatory group. I was part of that on behalf of the US and Canada, a European strategy group, and then a secretariat. And this body receives a charge, a mandate, and the mandate is presented above. So the aim of the strategy update was to develop a visionary and concrete plan that advances human knowledge in fundamental physics through a flagship project at CERN. And the plan should attract, of course, international collaboration. So the process started in September 2024. The community was invited to submit input proposals by March 31st. We had an open symposium in Venice, Italy in late June. All the inputs had been already presented there, summarized, and then the preparatory group essentially assembled all the input to try and understand what the community wanted to essentially build and provided the so-called briefing book, so the outcome of the studies, to the European strategy that met early December to deliberate. Canada did submit its own expression of interest, if you wish. It was based on a survey that was carried out in the country, and based on the input received, the submission indicated endorsement of the integrated program FCC-EE, FCC-HH. And as I said, the strategy group formulated and developed the recommendations that were presented to the council the second week of December. And the narrative reads as follows: the FCC-EE is considered capable of delivering the world's broadest high-precision particle physics program. It would pave the way towards a high-energy hadron machine, and it did receive overwhelming endorsement by the community. So the strategy secretariat highlights member and associate member, but also Canada and the US that are not associate member supported the FCC. So it really received worldwide support. Okay, to conclude, a fundamental question on the composition and the time of evolution of the universe do remain unanswered as of today. The Higgs boson, that of course represent a capstone of our somehow process in understanding nature, did open a new sector that has a deep implication well beyond the standard model, so it should be studied thoroughly at high level of precision. At the same time, theory and experiments seem to point to new physics below the 10 TeV scale, so we have to develop a very coherent strategy. So we want to have a precision, E plus, E minus measurements, plus a direct exploration of the energy frontier. So the LHC, it's operating now. It will offer a really unique data set between 2030 and 2040. It will extend our understanding and our reach. And then in terms of future collider, the US strategic planning did envision an offshore Higgs factory at CERN and a 10 TeV muon collider in the US. And the European strategy for particle physics identified the FCC-EE and FCC-HH, so the integrated program, as the most comprehensive path forward. And now we are in the hands, of course, of the CERN Council that is analyzing the input that they received. They are integrating, of course, financial consideration, and they will share their deliberation in the council meeting of the spring, so we will know whether or not the FCC will be, EE will be approved. Okay, thank you so much for your attention.
Thank you, Anadi. That was great. So there are a number of the questions, the and perhaps the I can just read them out, and you can perhaps answer them. So the first one was, how did you generate or find these cool images, such as the Higgs potential and that dark matter slide?
ChatGPT. And I wrote it. So I gave credit to ChatGPT on the slide, yes.
Okay. Uh, the second question was, how much work would be required to transition from the FCCEE to the FCCHH?
It's a good question. So the decommissioning is not too complex because the radiation level is not high. So it's a very different with respect, for example, to decommissioning the LHC. So they are talking about 5 years and the current, let's say, 2025 Swiss francs, approximately 300 million.
Okay. The next question is, speaking of the time evolution of the universe, when will these future machines produce data?
Okay, so it depends which one is built. So assuming it's the FCCEE, so the plan is to stop high lumi in 2041. We do need some time to cool down and then to decommission the machine. The tunnel, the construction of the tunnel will start in 2041, and then the plan is to start operation in 2046. So, of course, it's a relatively long time scale. At the same time, the high-lumi is producing a beautiful data set till 2041. It will take a couple of years to analyze it, so there is really no discontinuity in the scientific output of the CERN complex.
Great. Okay. So 20 years from now, perhaps the
Yes.
but you got to start working on it now.
Yes.
Um, the next question is from David Bailey. The LHC had a very clear justification since experiments were going to either discover the Higgs or observe the standard model breaking. How do you convince governments to fund an even more expensive new accelerator without any guaranteed discoveries of equal significance, without a no-lose theorem, I guess?
Yes. Of course, it's a very good question, right? So I think there is, first, we do have the hints, right, from a theory perspective, experimental perspective, the new physics may be below the 10 TeV scale. So that's why we are trying to assess whether technologies exist to build a machine that has high sensitivity at that energy scale. And that relates to the stability of the Higgs mass, the dark matter, the evolution of the universe. So all these elements seem to indicate that new physics should exist, and that otherwise we should introduce, let's say, fine tuning to keep the electroweak scale very low. It's not as strong as an argument as the Higgs, so we don't have a no-lose theorem at this point. I think we should follow two different paths. On one side, we should explain that indeed the 10 TeV scale is a special scale. And in parallel, we should really highlight that if we want to continue the exploration, it's really our ambition to continue scanning in higher and higher energy, and not, even though we are more expensive than other disciplines, none of the scientific endeavors have necessarily a no-lose theorem. So we should also change the conversation that we have with our funding agency. It's a challenge, I don't doubt it, but yeah, there is clearly no clear no-lose theorem at this point.
Right. But you don't find if you don't ask. There's
Exactly,
also
exactly. Yes.
the argument for that. David Curtin asks, can you give us a feeling for how likely the US is to take up the Muon Collider program in earnest?
Mhm.
And are there any timelines?
So from a community point of view, the community is ready to really engage in the muon collider. There is, if I may say, more enthusiasm and participation in the muon collider studies than for the FCC, for example. So the community has pushed, has embraced, and is really trying to make steady progress towards a muon collider. The situation is, of course, the funding. So at the moment, we do expect the DOE to primarily invest into supporting CERN because that is expected to start construction earlier than any potential muon collider because, again, we expect to start in data taking in 2045. And also in the US, we have a larger program, of course, LBNF Dune, that is a bit saturating the budget envelope for high energy physics. But we have a clear indication by P5, which recommends DOE, which is our funding source, to invest in the muon collider. So there is a commitment to allocate any possible funding that becomes available in that direction. It's important to highlight that the muon collider won't be the first step. What comes first is the demonstrator, which is in itself quite expensive because we are talking about 300, 400 million, but of course it's not the scale of a collider. And we hope to have a so-called CD0, so a conceptual design first stage in the 2030. So to have a design of the demonstrator in the 2030 and start taking that step. I think the community is ready. Fermilab is ready to host it. In my mind, it's the natural evolution of the lab and it should go in that direction, personal opinion. And it's a matter of really understanding when somehow we are over the major investment into Dune and we can start seeing some relaxation in the budget envelope.
Right. Okay. And I think right now the last question we have is from Rishab Mishra. What are some BSM physics, beyond standard model physics, we're currently on the lookout for, especially via the FCC? Are there any the credible theories that predict particles at those energy scales, which we have yet to observe?
So there is no prior, so I cannot tell you that one theory is most likely than another, right? It would inject my personal bias. We have almost any theory for standard model, beyond the standard model, sorry, can be tuned to address the current constraints, so to really adapt to a possible existence of particles beyond the scale we have explored at the moment. So there are a few that have been completely ruled out. For example, gauge-mediated supersymmetry breaking that has been completely ruled out after the discovery of the Higgs because it would clash with the mass of the Higgs. It would not predict that. But other than that, most of the theory for BSM are still viable, and it's a matter of really exploring and fine-tuning their internal parameters to the new energy scale.
Okay. Thank you very much. Anadi, this has been a really exceptional tour, not just, what we've been doing, but what we can be doing. And it's certainly been one that I found quite fascinating. You can't hear applause on these sorts of things, but let me just thank you
Thank you
on
so much for
behalf
the
of all of
invitation.
us.
My pleasure. Thank you so much.
Okay. And good luck.
Okay, thank you. Bye, everyone. Bye-bye.
Bye-bye.